Good evening to all of you. Myself Suresh Kannaujiya. I am scientist in Geosciences Department, IIRS. So today's lecture is advanced GNSS data processing. So we will discuss. So here is the outline of the lecture. GNSS observable, basic theory. Then we will move to modeling the observations and limits of GNSS accuracy, basic stages of GNSS in CAMET and Globe-K. So there are open source softwares globally available. So this software we use when we require millimeter or sub-millimeter accuracies for different application. Then at the end, we will discuss about the case study. So the pseudo range. What is pseudo range? So pseudo range is nothing but when our GNSS satellite transmit the electromagnetic waves in microwave range. So basically it is L1, L2, L5. So it comes in this range. So it carries different types of signal. It carries code signal and carrier phase. So basically, this is the distance when we are determining the latitude, longitude, and height based on distance calculation. So it is called pseudo range. So you can see here, satellite is orbiting at altitude 20,200 kilometer. So these are the code signal. So code signal is nothing but square wave. So it is very crude signal which we use to get the very quick latitude, longitude, and height. And here is the receiver generated signal and satellite received in the receiver. So it is not synchronous always, because there are number of error which causes delay in the signal. So we say it is t plus small t, and original time is t. So if it is if there is no delay, signal would be look like this, but actually it is not coming. We are not the receiver is not receiving like this. So there is a, that's why it is not a true range. It is a pseudo range. So we use this formula to estimate the range in 3 direction, X, Y, and Z direction. And you can see this is the satellite range, and this is the receiver, and these are the formula. So this is for satellite and this is for receiver, and this is the total time, CT. C is the velocity of light. And this is the general formula to estimate the range. So we know that we need 3 satellite to estimate the latitude, longitude, and height, which had been covered in the previous lecture. So time delay, it is the travel time measured by the clock in the satellite and receiver, which is subject to error between these clocks. So we know that satellite uses cesium or rubidium particles for the clock, and receiver, because these particles are very costly, so we use quartz particle in the receiver clock. And this is the point positioning. So when we go for point positioning, and when we need X, Y, Z, and time, so we need minimum 4 satellite, because we have 4 unknown. So that's why to solve the 4 unknown, we need minimum 4 satellite. And we can get 5 to 100 meter accuracy by point positioning, and by differential, we can get 1 to 10 meter. But without applying any error. Once we are going to apply the different error, which we will discuss in subsequent slide. So now we are going to discuss about the parameters. So first we will discuss about the satellite position, how we determine the position of the satellite precisely. So estimate precisely, we need Keplerian elements. And these Keplerian elements is determined the orbital parameter broadcast by each satellite as a part of its navigation measures. So this information we collect with the help of L1 signal. So there is suppose there is two signal N1 and L2. So we with the help of L1 signal course versus acquisition wave code, we estimate the navigation message. Now, what is Kepler law? So we know that there are three laws of planetary motion. The first law states that orbit of each planet is an ellipse with the sun at an foci. And second law states that this planet sweeps out equal area in equal interval of time. And third law states that square of the time is taken by the planet is proportional to the orbit cube of the orbit is proportional to the cube of its mean distance from the sun. So here's the schematic diagram which confirm or which clarify the three laws. So first law clears the orbital ellipse. So it always forms the ellipse. So it will have a perigee and OPG. So we know that closest near to the this planet is perigee, and farthest point is apogee. And second law states that law of equal areas. And third law, orbit with equal period. So it will always have equal period for one complete orbit. So why this Keplerian elements is important determining the satellite position? Because it determines the size and shape of the orbit and orientation in space, and six element specifies the position of the satellite at a particular instant of time or epoch. So here is the schematic diagram where it signifies our define the different parameters, how it appears physically in the space. And here is the table, how it help to describe the satellite position for different descriptions. So satellite and shape of the orbit is determined with the help of semi-major axis and eccentricity. Orbital planet in the apparent system determined with the help of argument of perigee and drift of node, and position of plane is determined with the help of mean anomaly. Here is some calculation. So if you want to calculate satellite orbital period, so we have to use semi-major axis. This is 42,242 kilometer. So we know the gravitational constant. So orbital period, the formula is this. So this is the estimation, 8.6164 into 10 to the power 4 second orbital period. And if you want to determine the angular velocity and speed of the GNSS, our GPS satellite, so it is 1.458 radian per second, and the speed of the satellite is 3874 meter per second. So if you want to calculate the maximum Doppler velocity, so it is 929 millimeters per second. So this is the mathematics behind the latitude, longitude, height, and time determination. So we use these equations to determine these four unknown. So x1, y1, z1, and time. And c is the constant factor, and t bias is the delay in the delay due to the different errors. So what are the different error sources in pseudo range measurement? So satellite ephemeris error. So it is nothing but your navigation and orbit error, satellite clock error, satellite receiver clock error, ionospheric delay error, troposphere error, multipath error, and other error. So there are so many other error also, which we will discuss in subsequent slide. So how generally how it can how much error it can produce? So these are the error range. So satellite clock error can produce 2 meters plus minus. Orbit can produce plus minus 2.5. Ionospheric can produce 5. Troposphere can produce zero point 0.5. So this is not the this reference level. It can vary, but it will vary in this range only. And multipath can vary 1 meter. So this can increase or decrease also. So these are the some standard values. And here is the diagram, schematic diagram, to explain to define the code and carrier wave. So code is nothing but this is the square wave and this is the sinusoidal wave. So if there is no very less error, so it will have a perfect sinusoidal wave. Code carrier will have such perfect sinusoidal wave, and this is the code wave. So we normally see in the L1 and course versus acquisition signals, and this we see in advanced GNSS receivers. So now we will understand the carrier phase observable, because here we are going to discuss about the millimeter processing. So that's why it is very much important to discuss the carrier phase observable. So we are going to discuss the theory behind the calculating the different parameters like ionosphere delay, troposphere delay, multipath error, receiver clock, satellite clock error. So all this, how it has, from where it has come up and how it has been driven. So we will see from one slide to another slide. So first we will understand what is phase. So phase is nothing but angle of rotation. It is the angle of rotation, so unit of cycle for GNSS analysis. So we can see this. It is this measure of time. So when there is some signal, so signal is going like this, like carrier wave. So it is varying in every fraction of seconds. So it is this is the formula. So phi naught is nothing but your phase at time 0, and phi t is the phase at time t, and this is the t naught, capital T into small t. So we want to calculate this t because we are never getting the actual phase which we want to determine the latitude, longitude, and height. So that's why we have to subtract phi t minus phi naught, and this is the angular speed. So this is the general formula of the angular speed. If there is an ideal clock, if there is no error at all, so it will behave like this. Phi ideal is f naught t plus phi naught. For therefore, t ideal will have t ideal. So here if we keep this here, so we will have f naught t. So where calibration k is the calibration constant and it is 1 by f naught. So finally we will get t small t, so phase t minus phase naught upon f naught if we keep this calibration constant here. So now we will utilize this formula in to derive the carrier wave. So how phase is related to periodic signal? So if you see this circle and if you see this phase at time t, so we can see that this is a naught. A naught is the amplitude and phi is the phase at time t. So this is the formula at a naught sine 2 phi t. So how it is related? Because this is we can relate this circle directly to square wave, and this complete one circle, this unit is your circle. So we can use this formula to derive the carrier wave. So when we keep this into here, so this is 2 pi phi ideal. So we know phi ideal is from the previous slide, from previous formula. So if we expand this, we will get this. And after expanding this. So this is the constant. So these are the constant. So A naught S and A naught C. So finally we will get this. So this is called your carrier signal. So A ideal is equal to this formula, and this is called carrier signal, where omega naught is the angular frequency. So this gives us precise access to the satellite clock time, and therefore we can use this phase for precise positioning. And now we will use this to derive the carrier beat signal, because ultimately we want this unit length. So how we can derive the unit length? With the help of carrier beat signal. So carrier beat signal is associated with your replica signal. So it is not only the satellite signal. So same time receiver is generating replica signal of the respective satellites. So that's why we have to use the cross correlation. And once we use the cross correlation, we have to keep like this. So we can keep this formula like this also. We know the trigonometry. So we have to apply the filter to remove the higher frequency component. So once we apply the filter to this formula, so we will get the this component only. It will remove it, and finally we will get like this. And phi bt is nothing but your phi r. Get fb is equal to fr minus fg. So now what is now we want to estimate the carrier phase observation model. So to estimate this, we have to expand this formula, previous formula, and here this is the satellite phase of satellite minus phi t minus small phi t. This is the receiver phase. This is the satellite phase minus errors. So satellite phase is the three component and plus time, which we are getting with the help of L1 signal. So we know this formula. So when we will keep for the satellite S, because here we have taken a particular satellite. So there are, for like GPS, there is 32 satellite. So like that, there are other constellation: GLONASS, Galileo, Bedu, like IRSS. So IRSS is nothing, is our regional navigation system, navigation constellation, and others are global navigation constellation. So phi t, when we will keep this formula in the this above formula, so we will get equation like this. So we will keep some superscript and subscript and superscript. So this subscripts we are keeping for this receiver, and superscript for satellite. So this is your superscript and this is subscript. So when we will keep for n number of satellite, so we will have equation like this. So this is the final equation for the error modeling, and this is the unit range. So this is the unit range, because ultimately we want the unit range, because it will help us. It will make it easy to determine the different determine the different component x, y, z, and t. So this is the final formula. These are the time clock errors, and these are the error due to the troposphere error and ionosphere error, and BJA is the error due to multipath error, your non-tectonic and tectonic errors. So we will discuss later on. And when we are going for single differentiating, we have to use this formula. So in single differentiating, we have to use the 2 stations and 1 satellite. So with the help of single differentiating, we can remove satellite clock biases. And in the double differentiating, we need 2 satellite and 2 stations. So with the help of this, we can correct receiver clock biases. So once now we will discuss GNSS data processing in Gamut and Globe K. So as I told you, there are a number of open source software. So this is one of the open source software which we can use to get the millimeter, our sub-millimeter accuracy, and we can apply all the error model to our acquired GNSS data, and this software process only GPS plus GLONASS data. It doesn't process other constellation data. It is only available for GPS and GLONASS. So we are going to understand how it help us and how it is working to estimate the sub-millimeter accuracy, achieving the sub-millimeter accuracy. So this is the diagram, estimated diagram for different satellites. So this is nothing but the signals of different satellites at a particular stations. So here we can see how phase is related to different time and range. So you can see because it is carrying number of tremendous information. So you can see this is the one predicted and one is theoretical for a particular satellite. So it is providing a tremendous information. So with the help of this information, we are going for this error determination. And this is the observable which we need to apply in the model to correct the different errors. So we know that L1 phase carries 19 centimeter. This one length, one complete length, one period is your 19 centimeter, and L2 phase is 24 centimeter. So C1P1 pseudo range used separately to get the receiver clock offset time. So here is the general formula for this linear combination, to correct the linear combination, to remove the ionosphere and geometry error and your troposphere error. So this is the formula. So you can see this formula. This is F12, and this is FL1, this is FL1, and this is FL2, this is FL2, this is FL1, this is FL2. So we have to use this formula for ionosphere and for your geometry and troposphere correction. So this is, we have to do the linear combination to remove the ionosphere correction, and we have to use this PC, this formula, to remove the geometry and troposphere correction. And as I told you, we use double difference, remove the clock fluctuation, and linear combination almost remove the ionosphere. So both, but what happens when we apply this corrections? So at same time it amplifies the noise, and it normally does for baseline less than 1 kilometer. So that's why at same time we have to check whether it is amplifying or not. So say we have to rectify all the amplification, and we have to restore to the normal condition. And this is the formula to edit the data and ambiguity resolution. So ambiguity resolution, we have to do this geometry free combination. So this is the linear geometry we use in gamut, and it removes all frequencies independent effect, geometry and atmosphere, but not multipath and ionosphere. So ionosphere can be removed with the help of these equations, and this we use to remove the geometry and ionosphere, Melbourne and Webner wide length, which is dominated by pseudo-range noises. So this is the formula, and this all works in the gamut software. So there may be different methodology for different software, but I am discussing only for the gamut, our GlobeK software. And when we are working with this modeling, so there are so many number of these motions. So like motion of the satellites, motion of the Earth, propagation of the signals. So these are the different source of errors. And like in motion of satellites, how it can induce. So Earth gravity field, attraction of moon and sun, solar radiation pressure. So it can induce your motion of satellite. So it can cause a huge error in the data. So that's why we need a model. We need all these models. So this we can easily get, but this may not we get a very precise model. So we need a long period data for this model to apply in our data to correct the errors. And motion of the earth. So motion, irregular rotation of the earth, lunisolar solid earth tides, and loading due to oceans, atmosphere, and surface water and ice. So this causes motion of the earth, and this induces the error in the signals, carrier wave signals. Then propagation of signals. This can be induced by ionosphere. It can be caused by ionosphere. Ionosphere, we know it is frequency dependent layer. Neutral atmosphere, it is nothing but your troposphere. It is frequency independent, and it has a dry component and wet component. And ionosphere having a very ionized layer where huge electron is present, and variation in the phase center of the ground and satellite antenna. So phase center, we know it is having, and at the center of the antenna of the ground station and satellite antennas. So this and this, it is very difficult to model precisely, but we have a model. So then modeling the observations. So we use all this model in the software to apply the corrections. So like SP3 file, like your this inertial space SP3 file, and then your IIRS, International Earth Rotation Services. We use this to get the axis rotation, pole position, all this model we get with the help of this website. Then we use a solid earth tide, global grid of oceans and atmospheric tidal loading. We use this model. Then we use zenith hydrostatic dry and delay from pressure, zenith wave delay, crudely model and estimated in solve. So we get very precise this model, but we may not get very precise weight delay, because it is very difficult to model the weight delay. And this we map to the line of sight with mapping function using GMT software, variation in the phase center of the ground and satellite antenna. So then we do the parameter estimation. So we do the number of parameter estimation, like double difference linear combination of L1 and L2 to cancel the clocks and ionosphere. Then we apply the a priori coordinate constant. Then we estimate the coordinate. Then we apply this model to correct the ionosphere, geometry error, troposphere. Then we estimate the coordinate. Then we make the batch, and we apply the least square to get the loosely constant solution. And then we get the H files, and we apply this H file in the Globecase software, and we get the continuous time series of our observations. And then we do the interpretation. Now comes to the limits of GNSS accuracy. So how it limits our GNSS accuracy? How different property limits? So this is signal propagation effect. So as I told you, say signal scattering, atmospheric delay, ionospheric effect, receiver noises, unmodeled motion of the stations like monument instability, loading of crust by atmosphere, oceans, and surface waters, and unmodeled motions of satellites also. So this, and then reference frame. Reference frame can also induce some errors in our estimated positions and time. So now we will discuss signal propagation effect. So signal propagation effect can be induces mainly by the multipath. Like you can see, this is the reflected signal and this is the direct signal. So direct signal is directly going to the antenna. So we know that this carrier wave, our electromagnetic wave, is coming right-handed polarized. It is right-handed polarized signal. So we normally use choke ring antenna. So when these reflected signals comes to the antenna. So due to the choke ring antenna, it reflected back again, and right-handed signal it converts into left-handed signal, propagation signal, and when it comes back to the antenna, it will not enter into our antenna because it becomes left-handed signal. So that's why we have to use choke ring antenna to remove the multipath effect. So here is the different height, and here is the this multipath combinations LC, and this is the elevation angle, how it is related. So we can see at low elevation angle there is a number of huge multipath error, but at high elevation angle it is having low multipath error. And here is the geometry schematic diagram, how it is signal is incident into the antenna, because this is the phase interrupt of the antenna, and this is the reflected signal, and this is the direct signal. So multipath contributions to the observed phase or for 3 different antenna height. So it is clear from this schematic diagram. And this is the atmospheric delay. So there are the number of satellites. So this is the horizon, and here elevation angle is 0. Here elevation angle is 90 degree, and satellite is distributed very nicely here, but it can induces due to the weight component and dry component. So which we need to correct precisely, because the weight component is not available precisely, but dry component is precisely available. So that's why we need to correct, and we have to make it to this zenith green bar. Then how it look like zenith delay from weight and dry component of the atmosphere. So when we have estimated this, so we can see the total delay is 2.5 meters, but the variability, we can see the variability. So this variability is mostly caused by the weight component. So this is not stable. So we have to make it stable. So we need a precise model to make it stable. So when we see the hydrostatic delay, only dry component, so we can see that this is having almost linear relationship with the time, but it is not having linear relationship with the time, because we see wet delay having huge variability. It is not having linear relationship. So that's why we need very precise weight model. Then multipath and vapor effect in the observations. So we can see that this is 12 to 18, 18 to 20, and 20 to 24 hours. How this we can see the multipath and water effect in different time interval. So we can see how it is increasing. So this yellow and green is positive and negative residual purely for visual effect, and red is the satellite track. And colors reflect the your increase and decrease in the multipath and water vapor effect. And this is red bar is the scale in 10 millimeter. So you can see if there is a huge multipath, it can cause huge error in our position. Then your others error. As I told you, others error. So others error are your this tectonic and non-tectonic error. So we already discussed the non-tectonic error. So this tectonic error due to linear rate, seasonal term, temporally correlated noise. So this is your water effect. So this is due to non-tectonic, and this discontinuous due to the equipment, our environment. Discontinuities due to the earthquake. This is tectonic. Non-linear motion due to earthquake. This is tectonic. Non-linear motion due to transient event. So volcanic inflation episode. So this is also tectonic event. So we will go one by one. So this is also cause perturbation in our signal. So derives from after sleep or on fault plane controlled by the rate and state frictions. Velocity perturbation reduces with 1 by t, and one exponential decays would be there. So we can see clearly that in logarithmic decay and exponential decay, non-linear motion. So this is non-linear motion. So there is the break in both the signal, but there is no break in the vertical motion. It is having seasonal variation. So we can clearly see that it doesn't affect the vertical, but it affects the horizontal motions, north-south and east-west component. Then earthquake. So earthquake can induce, you can see earthquake is occurring at different time interval, and it can induce and it can break our signals, but there is no break in the vertical component. Then groundwater variations. So during the monsoon time, wet ground may expand, uplift, but additional load create the subsidence. And in dry time, your may contract, subside, but it reduces load, also produces uplift. So this non-tectonic can create also error in our to get the millimeter or sub-millimeter accuracies. And this is the vertical loading globally. So now we have covered this parts and monument instability. Now we will cover unmodeled motion of the satellite. So this is mainly due to the non-gravitational acceleration due to the solar and earth rotation, unbalanced thrust, outgassing, non-spherical antenna pattern. Modeling of this effect has improved, but for global analysis remains a problem. Now the reference frame. So what is reference frame? Reference frame is nothing but the physical realization of reference frame. So requires fixed measurement site. So there are globally 500 plus sites which we use to get the reference frame in International Terrestrial Reference Frame. So it uses the position and velocity in the reference frame and thus constitute realizing the system, VLBI, SLR, and like GPS and other constellation it uses and make the datum. So it's nothing but it is a datum like WGS84. So there are some other datum also. So this is this text from the center of the earth because we need one reference position. So reference position is the center of the earth. So with the help of geometric geocenter, we can estimate the ITRF. So how well can you relate your position estimate over the time? So it is a set of station whose motion is well modeled, a set of crust that allow you to interpret the motion, and how to use the available data and the features of globe K to realize the frame. So we normally do because when we process the data, we get the loosely constant solution. So we took this loosely constant solution into globe K, and there we apply the Kalman filter, and we also set up the reference frame, and also we fix the stations. After doing all this, when we apply this this script to our process data, we get the continuous time series of positions in three directions: north, south, east, west, and vertical directions. So basic stages of GNSS. So first we do the data collections. So if you want to process your data precisely in Gamut software, we have to collect at least 8 hours. If you are collecting data less than 8 hours, you cannot process your data in Gamut software, and also you cannot achieve millimeter accuracies. So you need minimum 8 hours data. And if it is more than 8 hours, there is more than sufficient, but you need at least 8 hours. So then you have to convert into RINEX file. RINEX is nothing but your receiver independent exchange format, so which you can convert with the help of convert to RINEX, taxi, our spider software. Then you have to process your RINEX data in Gamut software. You have to apply different correct models. Then you will get the H file. So H file you have to apply into the GlobeK software, and there you will get the time series and velocity, and with the help of GalRad and GlobeK. So GalRad provide you the time series, means continuous this deformation, and GlobeK provide you the velocity of the site. Excuse me. Excuse me. Basic input and output. So Rhinex data must be prepared to input into the gamut, and output gamut and input to GlobeK are H files, as I told you. So loosely constant solution with a priori parameters information which we get with the help of gamut and parameter adjustment and full covariance matrix. All this we get from the gamut, and final output will be time series and velocity from the GlobeK. And before processing, this is p-fit. So we have this data, this into 10 to the power 3. You can see how much error it is associated. But after the processing, a post-fit, you can see this 10 to the power 3 has been removed. And this is constant free, this is constant fixed, this is loose free, and this is loose fixed. So you can see all has been removed and all are in sub-millimeter or millimeter accuracy. And we can see here how much double difference has been applied to the data. It is 124.47. And number of WN and LL biases, it is 120. Then 95. And when we do all this processing, so how much confidence you have? So when you process this data, how much confidence you have? That confidence means what you have estimated, how much accurate it is. So it is 95% error ellipse. So 95% it is correct. It cannot go beyond 95%. So it will suppose it is, if it is having 0.2, so it will range plus minus 0.2 only. It will not go beyond that. So this is the confidence level when we process our data in gamut. So this is the beauty of gamut software. Any large adjustment to produce greater than 0.3 meter. So things to be noted. So number of station matches expectation. So number of post-fixed RMS should be 3 to 10 millimeter. Or less than that, number of station with RMS 0. It means no data retained by autoclean. So post RMS solve 0.2 constants and loose solutions. And most navigative solves 70 to 85% for noisy day and greater than 90% for best day. So noisy day can be your like if there is a rainfall, it can produce 70 to 85% and some other, and due to some other also. And if it is perfect sunny day, it will have greater than 90% for best. And this is the side which clear you the phase residual plots. So here you can see how the error is reducing with the increasing of elevation angle. So if you are having data with this range, with this elevation angle, so it will have less error, less phase. And also if you have long period data, you will have less this phase error and more information. So here we will discuss continuous and campaign GNSS data measurement for strain and crystal deformation modeling in the Himalayan region. So how I will discuss how this gamut GlobeK software and this parameter has been utilized to remove the error from the continuous and campaign GNSS data measurement to achieve the millimeter to sub-millimeter accuracy to derive the strain and crystal deformation modeling, because this strain is very in Himalaya. This rate of movement is very slow. Rate of movement is 50 millimeter to 30 millimeter per year. So rate of movement is very, very slow. So it is, if we are not able to estimate sub-millimeter or millimeter accuracy, so we cannot determine crustal deformation or strain in the Himalayan region. So that's why it is very, very important to apply all these corrections to get the to achieve the required accuracies to determine the strain and crustal deformation. So this is the study area. So here there are the campaign stations, and some of the permanent stations. So these are the this magnitude and epicenters of the earthquake since 1910 to present. And these are the fault. These are the different thrust, HFT, MBT, MCT, then Sangpo Suture detachment zone, then Karakoram fault. Then here you can see the zoom image, which clear you this campaign stations and permanent station. Permanent station you can see here also. So now we have 14 permanent station and 27 campaign stations around. So, and you can see that they are distributed nicely because we want to map the strain and crustal deformations. So we want to do a time series analysis as well as map analysis. So for this, we have set up this permanent station. So we can see this is very good example of permanent station. This is set up by IIRS. And like that, we have 15 stations. So you can see this monument, antenna, housing. Housing is used to keep the receivers, and then this is the solar panel to provide the power to the receiver and antenna. And this is the MET sensor because we have to model the troposphere. So we need to have three component this temperature, pressure, and humidity. So this can be measured by the MET sensor. This is the geology of subsurface cross section across the Himalaya. So we can see the number of thrust and the main detachment zone also. It's look like a RAM zone, and it is currently earthquake is occurring from this area, and it is having approximately 20 kilometer seismic zone, seismic belt, and HFT and MBT is locked. So we have to estimate precisely the strain and crustal deformation to know what is the present scenario in the MBT and HFT. This is the campaign stations. So these are the campaign stations. So we have to mark one nail, we can keep one pin, and we can focus. We can keep our antenna just above the pin, and we have to center it, and then we can do the continuous measurement. So we do this measurement for 3 to 5 days because we are doing for crustal deformation and strain modeling. So that's why we need to do this 3 to 5 days campaign survey. Then only it will be focused by people, and it will be considered by the authors and reviewers globally for this research work. Then this is the continuous time series of north component, east component, and vertical component. So you can see this is the per day this position of a Dehradun station. So you can see it is going continuously up. It is going up north component as well as east component because our Indian plate is moving toward northeast. So that's why both are going toward up directions. But you can see vertical component is having sinusoidal component. It is moving sinusoidally. So this is happening because of hydrological loading. But here, this we have to rechange it because this is the circular component. So we have to rechange it to see whether they are also having the seasonal trend or not. So if you detrend, you will get the seasonal component. But for vertical component, you may or you may not have to do the detrend because you can directly see the seasonal component, compaction and contraction, expansion and contraction you can see here. So like that you can see for Mandal station, which is available in Chamoli region, and you can see the breaks. You can see the breaks also. So this breaks is due to data is not available for that period because due to the technical fault in the antenna, because they are very high altitude and temperature is very high. So it is very difficult to keep 24/7 active to the equipment. So sometimes it get the technical fault. So we have to solve as soon as possible to keep and to make it continuous. Then we can see that error. These are the error bars. So we can see more error here. There is also error bars, but we cannot see. Why we cannot see? Because error is very less. It is sub millimeter to sub millimeters. So that's why we are not able to see in the north, south, and east, west component. But we can see in the vertical component because here error is your 5 to 10 millimeter. So because of this error, it means is per day. So if you add all the days, means 5 months, 6 months, if you are going to add up, so average error will be less than sub millimeter. But per day error is your 5 to 10 millimeter, and here also 1 to 2 millimeter. So that's why you are not able to see here, but you can see in the vertical component in all the stations. Then these are the campaign stations. So here also you can see that these are going up. So this is 3 time period. This is acquired in one time, this is another time, and this is another time. So all the time you can see they are going up. So if you are getting trend like this, so it indicates that you have done correct measurement. So because it is having linear relationship. So it confirms that you have done measurement. You have done the center. Your instrument was rightly centered and labeled. So because of that, you have got linear relationship in all the component, in all the stations. So it confirms that we can also achieve millimeter accuracy in the campaign stations. Then you can see the velocity of different stations. So Bangalore and Hyderabad is the IGS station. It is international GNSS services. So there is 500 plus GNSS stations globally, and data is free of cost, which you can use for your applications. And in India, there are 3 IGS stations. One is in Bangalore, another is in Hyderabad, and one is in Lucknow. So there are 3 IGS stations available in India. And you can see the north component velocity and east component velocity. And the error, you can see it is in millimeter. So you can see they are in sub millimeter error velocity. And this is Port Blair station. And then you can see our data also, they are also in sub millimeter accuracies. And these are the velocities. And we have done this comparison also, campaign data and continuous data, means permanent station data. So CORS is also known as continuously operating reference stations. So you can see both are matching together. Both are very close to matching together. So it confirms that campaign data is as good as CORS data. And then these are the location X, Y, and Z data. And these are in geocentric coordinate. These are also called geocentric coordinate. So, and also you can see this is in meter. So if you calculate in millimeter, so these are in millimeter accuracy, some millimeter accuracy. So this is what the beauty of different model. So once you apply the model which we have discussed in previous slide, so you will get your parameter in these accuracies, and you can give your 100% confidence to your result that what you have get it is correct. You have 95% confidence ellipse. And this is the crystal shortening which is happening in the Himalayan region. So we can see it is 12 millimeter per year. So this is in Malari, and this is in your Dehradun stations. So this is 12 millimeter, means 12 millimeter is crystal shortening is taking place in the Himalayan region. So it is not releasing the energy. It is maybe it is uplifting, or it is contracting, but it is not releasing the energy. It is strain is increasing and day by day. And these are the vectors of different stations, and this is for India as well as our local stations. So you can see that all stations are moving toward northeast, and this is the strain component, extension and compression. How much extension is taking place? How much compression is taking place? So we can see. So here, expansion and contraction less, and but here you can see compression and extension is more. So in MCT region, main central thrust, it is more. Here it is less, and these are the strain components. So this is in HFT and MBT region. So it is their deformation is very less, and deformation is very high in MCT zone, and velocity is decreasing in MCT zone. And here it is more. Here it is less. And this is the linear strain. So we can see more strain is accumulating in MBT and MCT region, but in MCT region strain is releasing, and we can see both relationship, extension and compression. We can see both are happening in MCT region, but we can see in MBT and MCT, HFT and MBT, only compression is taking place, but in MCT, extension and compression both are taking place. And this is the altitude elevation cross section of the cross section taken from Bangalore to from Delhi to Malari, and this is the historical earthquake in this region, in this profile, along this profile. So we can see that it is validating that more strain but less earthquake. So more earthquake is going to be occur in future from this region, and here you can see more earthquake is taking place and less strain we can see. So strain is releasing here because more earthquake is occurring here. So this confirms and this validate our result. So these are the summaries of the result, and these are the some references which you can use for your study. Thank you very much.
Good evening to all the course coordinators and course participants in this 85th and 87th outreach program, which covered various lectures on GPS. So we have covered the basics of GPS, and then the GPS receivers, formats, satellite-based augmentation system, then the Indian Regional Navigation Satellite System, Gagan. So today we have actually telecasted the recorded lecture of Shri Suresh Kannaujiya as because of health reasons. However, tomorrow during the panel discussion, hopefully we will be able to take up questions on today's topic also. So with this, actually today we will complete the lecture series in the 87th course or the second module of 85th course. So any queries are there, we will take it up tomorrow in the presence of all the faculty members for the course. So I hope all the course has gone well. The lectures has been put in the LMS, so you can take out you can download the all the PDFs of various lectures which has been there in this course. Examination date will also be announced soon, so you can prepare for the exam purpose also accordingly. So tomorrow kindly join us at 4 o'clock for the panel discussion and remaining queries in this course. So thank you.